So good morning everybody, myself Acharya Vishvendra, and today I'm going to uh, start a video. It's basically a sort of one short lecture for some topics of modern physics. So let's start. So the first topic that we are going to do is photoelectric effect. So as you know that photo stands for light and electric means for electricity. So talking in a layman language, when there is electric current produced due to impact of photons or light, then that effect is called the photoelectric effect. This effect was observed by Henrik Hertz when doing experiments on conduction of electricity through gases in vacuum tubes. And he just observed that the sparking between the electrodes increases substantially when the cathode was irradiated with UV rays basically. So that showed that somehow UV radiations facilitated the emission of electrons from the emitter or the cathode. So from there the concept came, and then experiments were done by Henrik, uh, this Holwach and Dennard, and its explanation was done by Sir Albert Einstein in 1905, for which he got Nobel Prize in 1929. So this is a brief historical introduction about this. Let's study the concepts over here. So suppose this is the metal plate, and on the metal plate there are electrons. So when photons fall on these electrons, they are emitted. They leave the surface of the metal if they have sufficient kinetic energy to overcome the work function. We name these electrons as the photoelectrons. So we'll study in a very optimal to the point way. So the first point is conditions for photoelectric effect. So the conditions are that energy of the photon should be greater than the work function of the metal. And this can be equivalently said that frequency should be greater than the threshold frequency. And the same expression reduces to wavelength should be less than the threshold wavelength. So as per the first condition is concerned, we have three cases. Energy of photon should be greater than work function. Second condition is frequency should be greater than threshold frequency. And third is wavelength should be less than the threshold wavelength. Now let's study point number two. So point number two is the relation between these things. So the work function is related to the threshold frequency by phi naught is equal to h mu naught, which is ultimately related to the threshold wavelength by hc by lambda naught, which reduces to 1240 electron volt angstrom by lambda naught. This can be used as a shortcut to solve your questions. Then there is another thing that if these three conditions are satisfied, only then photocurrent will flow, otherwise photocurrent will be zero. Now let's study some graphs related to the concepts that we have discussed. So first is graph between phi naught and a nu naught, that is graph between work function and the threshold frequency. So obviously they are related by linear equation. So graph will be a straight line. So we can say that on increasing the threshold frequency, work function increases, and also vice versa. On decreases, it decreases. Then at second point we have graph between work function and lambda naught. So obviously they are inversely related. That means on increasing work function, threshold wavelength decreases and vice versa. And graph will be a rectangular hyperbola. However, if you draw graph between phi and 1 by lambda naught, so you take 1 by lambda naught as x. So we have phi naught proportional 1 by lambda naught, which is x. So we have the relation phi naught proportional to x. So the graph will be a straight line as shown over here. Now the fourth point is relation between the maximum kinetic energy of electrons. So first understand the concept. Suppose this is an electron and this is a photon, and photon has energy E. So when this photon collides with this electron, it transfers its complete energy to the electron. Now this energy gives electron kmx, and it has to overcome the attraction from the metal crystal phi naught. So we can say that E is equal to kmx plus phi naught From there we get k is equals to E minus phi naught as the expression. So that is how the expression came over here. So let's think in terms of graph. If we draw a graph between kmax and phi naught, so that will be kmax and E. So obviously that will be a straight line, and on increasing E, kmax increases, and on decreasing E, kmax decreases. So the graph will be a straight line having a slope 1 or the slope angle 45 degree and having the intercept as phi naught as given in this question. Then we have the relation between kmax and the frequency. So again the graph will be a straight line, and slope angle is equal to theta, where tan theta equals to h. Then if we draw graph between kmax and 1 by lambda, then again the graph will be a straight line having intercept as minus of phi naught. So these are the graphs. Now let us analyze the graphs of kmax and lambda. So from here we can see that there is inverse relation graph. So shape of graph will be rectangular hyperbola, and at lambda is equal to lambda naught, kmax will be 0. And since no photoelectric effect is possible for lambda greater than lambda naught, so graph will be limited to this point. We can also say that if lambda increases, then kmax decreases, and kmax decreases, then vmax also decreases. And if lambda decreases, then kmax increases, and then vmax also increases. So this analysis we can make from the graph. Next is graph between kmax and frequency. So suppose there are two different metals A and B. They make angle theta A, theta B. So obviously tan theta here is same for both because it is h. So both angles will be equal, and as we can see that intercept of second graph is greater than that of first. So phi b greater than phi a. And if phi b greater than phi a, that means threshold frequency for B will be greater, and that means threshold wavelength will be lesser than that. So you can draw the graph like this. Then we have graph between kmax and 1 by lambda. So that will again be a straight line with the same parameters. Then there is one important relation that kmax is equals to EVS, where Vs is the stopping potential. So the graph will be a straight line, whereas for lambda the graph will be rectangular hyperbola as given over here. And as you can see from the graph that lambda naught for B is greater than that of A. Since lambda and frequency are inversely related, so we can say that threshold frequency for B will be less than that of A. So these three inferences we can make, and work function is directly related to threshold frequency, so the same relation will be valid for the work function as well. So next on now we have the experimental demonstration of photoelectric effect. So it was done by Holwach and Leonard. So this is the vacuum tube, this is the cathode or emitter, this is the collector. So electrons are emitted, and we just connect this system to voltmeter and emitter and measure the relationship between voltage, current, frequency, wavelength, intensity, stopping potential with different parameters, and then we'll analyze their result. And these results actually proved that wave theory of light is not able to explain the results of photoelectric effect. So that is at what point the photon picture of light came into existence, and we'll discuss that in the next video. Thank you.